Hello viewers, today we will be taking up some of the important topics of the second unit, that is based on liquids. Lecture plan for today's lecture is introduction of surface tension, its concept and its determination. Then we will be learning about concept of viscosity of liquids and its determination. We will also learn to determine coefficient of viscosity. We will also learn about effect of temperature on these two properties, surface tension and viscosity. And we will be discussing about many live examples around us. Now to start with surface tension. Before going into details about the concept of surface tension, we will see many examples around us where we see this property plays very important role. We see that how dew drops stick to the grass and they do not spread. So, it is the surface tension which prevents it from spreading. We also see that many flowers float on the surface of the water. We also see that how water strider is capable of walking on the surface of the water and paper clip does not sink. So, it is the surface tension which plays very important role behind all these observations. Surface tension is an effect within surfaced layer of a liquid that causes the layer to behave as an elastic sheet. Because of the elasticity, it tries to contract. It is the effect that causes capillary action. This is caused by the attraction between the molecules of the liquid. As we know, there are many type of intermolecular forces acting between molecules of the liquid. These intermolecular forces are collectively called van der Waals forces. These are attractive forces and they act between electrically neutral molecules. In the liquid, we know that molecules are at moderate distances. Principal kinds of intermolecular attractive forces are dipole-dipole attraction, London forces, hydrogen bonding. These forces are attractive and they act between electrically neutral molecule. In liquid, we know that molecules are lying at moderate distances. Now, what are the different type of intermolecular forces which play important role? Right now, we will not go into detail about these forces as these have been already discussed in detail in other sections. These are the forces and their relative size play very important role in the property of surface tension. Now, we will further explain what is the surface tension. Now, here we can see this example. We have taken water or any liquid in a beaker. Now, some molecules are lying inside the bulk and some molecule which are present on the surface of the liquid. Now, molecule present here experiences intermolecular forces of attraction in all possible direction. So, overall net result is there is no force at all because these forces are in opposite direction. So, they will be cancelled. Now, we will see the position of the molecule lying on the surface. These two forces are in opposite direction, so they will be cancelled, but other molecules which are lying inside the bulk of the liquid, they will be attracting this surface molecule towards inside. So, overall a net inward pull is acting on any molecule which is lying on the surface. It is this net inward pull which is always trying to attract this surface molecule towards inside of the liquid is responsible for the surface tension. Therefore, surface of the liquid is always under tension and it is behaving like an elastic sheet. It tends to contract to the smallest possible area in order to have the minimum number of molecules at the surface. So, it is because of this property to shrink that in air drops of a liquid assume spherical shape, because we know for a given volume a sphere has a minimum surface area. Now, we can define the surface tension. The surface tension, as we have just learned, that it is the force, it is the inward pull in dynes acting along the surface of a liquid at right angle, because it is the inward pull. So, at right angle to any line of 1 centimeter length. So, this is basically force acting at per unit length. From here we can derive the units of the surface tension. As it is clear from the definition of the surface tension, unit of the surface tension in CGS system will be dynes per centimeter, and in SI system unit will be Newton per meter. These units are related as 1 dyne per centimeter will be equal to 0.001 Newton per meter. Now, we will understand the effect of temperature on surface tension. A change in temperature causes a change in the surface tension of a liquid. But how? We know when we increase the temperature, there is an increase in kinetic energy of molecules, because kinetic energy is proportional to the temperature. Therefore, intermolecular forces of attraction acting between molecules will be decreased. Since we know intermolecular forces were playing very important role in the inward pull, therefore, decrease in the intermolecular forces means decrease in the inward pull, and overall we can say that surface tension decreases with increase in temperature. Ramsay and Shields derived the following relationship to explain the effect of temperature on surface tension of any liquid. We can see this is the surface tension gamma m upon rho to the power 2 by 3. This factor is the molar surface energy of a liquid. Then this K is the constant, which is also known as temperature coefficient. Tc is the critical temperature for any liquid, and T is the temperature at which we are performing the experiment, minus 6. So, here it is very clear from this relation that this surface tension gamma is related with minus T, means as we are increasing temperature, surface tension will be decreased. Here we can see effect of temperature with the help of this table also. In this table, surface tension of many liquids, water, ethyl alcohol, methyl alcohol and many more have been reported at various temperatures 20 degree, 40 degree, 60 degree and 80 degree Celsius. Surface tension has been reported in dynes per centimeter. So, it is very clear from this table that in case of water we can see As we are increasing temperature from 20 to 40, then 60, then 80, surface tension is decreasing from 72.75 to 69.56, and like this finally it is decreasing up to 62.61. So, a decrease approximately of 10 dynes per centimeter. In the same manner, we can see in case of other liquids also a decreasing trend is there. In case of all the liquids, we can see from the values very clearly. Now, coming to the experimental part for the determination of surface tension of any liquid. Drop formation method has been very common for the experimental determination. For this purpose, we use this apparatus which is known as stalagmometer. This is basically a glass pipette with a capillary at the lower part. We can see here this lower part is having a fine capillary inside it. This is also called drop pipette. A drop of liquid is allowed to form at the lower end of the capillary tube here. Now, this drop is supported by the upward force of surface tension, because we know surface tension is the inward pull. Since we have filled liquid in this apparatus, so at this point drop will be experiencing inward pull. Now, its weight will be acting downward. When the two forces, downward force of weight and inward pull due to surface tension, they are balanced, slight crossing of the downward pull and dropping of the drop takes place. It is at that point of the breaking, weight of the drop mg will be equal to 2 pi r gamma. Gamma is the surface tension. 2 pi r, we know it is the circumference. M is mass of the drop and g is the acceleration due to gravity. Here r is the outer radius of the tube. Now, we can further see here from this diagram that how this drop is being formed at the lower end of the capillary and the inward pull due to surface tension. It is acting in this direction and the downward force due to weight of the drop is acting in opposite direction. Now, we will determine the value of the surface tension with the help of drop weight method. In this method, about 20 drops of the given liquid are received from the drop pipette in a weighing bottle and it is weighed. Now, since we have weighed 20 drops, so we can calculate weight of 1 drop. The drop pipette is again cleaned and dried. It is filled with a second liquid which is reference liquid. Generally, we take water for that purpose, and weight of 1 drop in the same manner is calculated. Now, from equation 1, we can see for the first liquid m1g is equal to 2 pi r gamma 1. For the second liquid, this equation becomes like that. Since we are using same apparatus, so this radius will be the same. Now, we will divide equation 2 by the 3 and then we will reach here gamma 1 upon gamma 2, this is the ratio of the surface tension, will be equal to m1 upon m2. Now, knowing the surface tension of the reference liquid, that is water, with the help of standard table, we can calculate the surface tension of the liquid under study. Since we have already calculated m1 and m2, that is mass of the one drop of two liquids. Now, another method which is known as drop number method. Here again we will take same stalagmometer and then this is filled up to mark A with the experimental liquid, say liquid number 1. The number of drops is counted as the meniscus travels from A to B. Drops will fall from this point. So, we will count the number of drops. Then we will again clean the stalagmometer and then we will fill it with the second liquid, and in the same way for the same quantity from A to B, we will calculate the number of the drops of the second liquid. Now, the volume of one drop of the liquid 1 will be equal to total volume, because total volume is constant for both of the liquid. Since we are measuring the experiment, we are performing the experiment with the help of same apparatus, divided by number of drops formed with the liquid 1. Similarly, the mass of one drop of a liquid, we will multiply it with the density. Then with the second liquid, we will be doing the same thing, V upon N2 multiplied by the density of the second liquid. Now we will divide these two equations and finally we will reach gamma 1 upon gamma 2. This will be cancelled and finally equation will become N2 D1 upon N1 D2, where N2 is the number of drops formed with the second liquid, N1 is the number of drops formed with the first liquid, D1 is the density of the first liquid and D2 is the density of the second liquid. Now this D1 and D2 we can calculate with the help of pycnometer. Now knowing the value of the surface tension of the reference liquid, since we are already knowing the values of N1 and N2, we can get the value of the surface tension of the unknown liquid, that is gamma 1. Now after learning the determination of the surface tension, we will see the applications of the surface tension. Surface tension of soap solution is less. That is why it can spread over large areas and wash clothes more effectively. In soldering, addition of flux reduces the surface tension of molten tin. Hence, it spreads well and will do its action properly. Antiseptics like Dettol have low surface tension, therefore, they spread faster and they kill germs more effectively. Surface tension prevents water from passing through the pores of an umbrella. A duck is able to float on water as its feathers secrete oil that lowers the surface tension of water. So, we can see that how much important surface tension is. Now coming to the second very important property of liquids, that is viscosity. Now viscosity is basically related with thickness of any liquid. As we know, liquid may be considered to be consisting of molecular layers arranged one over the other. When a shearing force is applied to a liquid, it flows, but a force of friction acts between the layers, and it is this force of friction which resists its flow. So, viscosity of a liquid is a measure of its frictional resistance. Now, let us examine a liquid flowing on a glass surface. The molecular layer in contact with the stationary surface, that is glass, has zero velocity. Now, the successive layers above this glass surface move with increasingly higher velocities in the direction of flow. Here we can see with the help of this diagram, this is the layer of the glass surface. This liquid we have poured on the glass. These are the various layers. So, this layer which is just in touch with the glass surface, this will be stationary, and as we move upward, layers will flow. Now, here we can further understand with the help of this diagram. This is the area of a particular layer and this is A, and this is the distance between the two layers dx. Now, consider two adjacent moving layers of a liquid. These layers are having a velocity difference of dv. Now, suppose this is moving with velocity v, then as we move upward, velocity will be increasing. So, this will be v plus dv. Now, frictional force which is resisting the movement of the layer is directly proportional to this area, that is A, and it is also directly proportional to the velocity difference dV, but it is inversely proportional to the distance between the two layers, that is dx. So, we can summarize these three observations into form of this formula F, that is frictional force, is proportional to A dV by dx. Now, F will be equal to, removing this proportionality constant, eta A dV by dx. Now, this eta, this is nothing but viscosity coefficient. Now, we can write this equation as eta is equal to F upon A multiplied by dx upon dV. This is simply the viscosity of a liquid, and it has a specific value for a given liquid. It is characteristic of that liquid at a particular temperature. It may be defined with the help of equation. The force of resistance, we can see this with the help of this equation also. Force of resistance acting per unit area, which will maintain unit velocity difference between two layers of liquid at a unit distance from each other. So, if value of A, value of dx and dV all are unity, then eta will be equal to F, means force of resistance will be equal to viscosity of the liquid. Now, reciprocal of the viscosity is called fluidity, means tendency to flow. It is denoted by phi. Now, coming to the units of the viscosity. The dimensions of the coefficient of viscosity eta may be derived with the help of same equation. If we put F is equal to force, A is equal to area, and then here distance and velocity, and finally we will arrive at this equation. Force means mass into length into time to the power minus 2, area means square of the length, and then here velocity and distance. So, overall units of viscosity will be mass into length inverse into time inverse. Thus, in CGS system, units of the eta will be gram per centimeter per second, and it is known as poise. In practice, however, smaller units are more common, centipoise and millipoise. As it is clear, centipoise means 10 to the power minus 2 poise and millipoise means 10 to the power minus 3 poise. SI unit of the viscosity is kilogram per meter per second. 1 poise is equal to 1/10 of the SI unit, that is being given here 0.1. Here in this table we can see the coefficient of viscosity of some liquids at 20 degree Celsius. Here in this column viscosity in CGS units and here viscosity in the SI units. From this table we can easily see that how viscous these liquids are. We can see benzene is having very low value. So, benzene is very thin, we can say it will flow very easily as compared to water. Here we can see glycerin, it is having very high value 14.9. So, that is why it does not flow well. We can see value of the viscosity for other liquids also. Now, how we will measure the viscosity for a liquid? Ostwald method have been the most common method for its determination. Viscosity is determined with the help of Poiseuille's equation. This expression can be written as eta is equal to pi capital P r to the power 4 T upon 8 LV, where V is the volume of the liquid flowing through the capillary in time t, P is the pressure head, R is the radius of the tube and L is the length. So, we can see in this equation many are the constants. Experimental measurement of P, R, L and V, they offer difficulty. Therefore, it is not possible to find the absolute coefficient of viscosity right away from this equation. Generally, what is done, viscosity of any liquid is determined with respect to viscosity of the water, and that is why it is called relative viscosity. Now, suppose T1 and T2 be the times of the flow of a fixed volume, because we are taking same apparatus here, volume V of the two liquids through the same capillary. The expression for the relative viscosity eta 1 upon eta 2 becomes like that. We will divide these two and finally P1 T1 upon P2 T2. Rest will be cancelled. Since the pressure head is proportional to the density of the liquid, this equation finally becomes d1 T1 upon d2 T2. Substituting the value of the viscosity coefficient of water eta 2 here, we can find the absolute viscosity for a liquid eta 1. Now, this is the Ostwald viscometer. This is Ostwald viscometer, is having two limbs. Left hand limb is essentially just like a pipette. In this limb there are two marks, one here A and other is here. Now, liquid is poured from here, right hand limb, and then it is sucked from the here. Then it will rise up to the mark A. Suppose we have taken first liquid, then we will allow it to drop, we will release it. So, liquid will travel from A to B and we will note down the time taken during this flow. Suppose that is T1. Now, we will repeat the same experiment with the second liquid, that is reference liquid, which we have taken to be water, and then again we will release it from A to B and we will note down the time taken. Density of the two liquids, unknown liquid that is D and water, are determined with the help of pycnometer. Now, relative viscosity coefficient is calculated from the expression here, knowing the value of viscosity coefficient of water eta here. At the temperature of the experiment, the absolute viscosity coefficient of liquid can be determined. Now, we will study the effect of temperature on viscosity of a liquid. In general, viscosity decreases with increase in temperature. Now, this variation can be represented with the help of this relationship. Eta is equal to A e to the power minus E upon RT. Here A and E are the constants. Now, we will take log on both sides and we will get ln eta is equal to A plus E upon RT, or ln n is equal to E upon R multiplied by 1 upon T plus A. We have written second part first and then this portion here. Now, we can compare this equation with the standard equation of a straight line, that is y is equal to mx plus c. So, m will be equal to E upon R, x will be 1 upon T and this c intercept will be A. So, we will plot y on the y axis, that is log eta, versus 1 upon T, that is x axis, and then we will get a straight line having slope equal to E upon R. It has been also found that there is 2% decrease in viscosity for every increase in 1 degree of temperature of a liquid. However, in case of vapor, reverse trend is observed. Now coming to the applications of viscosity. It governs the nature of liquid. Liquid will flow or not. We can see water flows easily, honey does not. So, honey is having higher viscosity than water. It also tells us about workability of a substance. Adhesive power of a substance can be increased with the help of knowledge of viscosity. It also plays role in setting process in many civil applications. So, we can see that how important these topics are. So, at the end we will revise what we have learned today. First of all, we discussed about the significance of surface tension. We also learnt about its concept and its determination. Then we also discussed about the important property of liquid, that is viscosity, determination of coefficient of viscosity and its applications in our daily life. We also discussed about effect of temperature on surface tension and coefficient of viscosity of a liquid. Hope it would